Hello everyone, today I'm going to share our work called AIFORE, a smart fuzzing solution based on automatic input format reverse engineering. Fuzzing is an efficient technique for finding vulnerabilities in programs. Typically, fuzzing produces a large number of inputs and feeds them to programs under test, detecting security violations. A smart and effective fuzzer relies on a high quality of inputs, which enables efficient exploration of the program state space and increases the chance of triggering vulnerabilities. And knowledge of the input format is essential to generate high quality inputs. The input format describes how the program expects the input bytes to be organized. Following the input format, the fuzzer can bypass sanity checks efficiently, reach and test the deeper code. Besides, the inputs against the format can test the sanity mechanisms and reach abnormal program states with higher possibility. Let's take how the program readelf parses the inputs of ELF format as an example. We can see that there are two main steps to parse the input file. The first step is to read the input and initialize certain variables corresponding to the input fields. For example, the first function loads the file header.emachine field. And the next step is to further process these initialized variables in the next function. Different basic blocks are used to process different types of variables because the basic block is the minimum unit in the control flow. For example, the 4-byte magic number is compared 1 by 1 byte, and the emachine is handled as an enumeration with a switch case statement. Thus, we have observations. First, bytes in an indivisible field are parsed together in one basic block. Second, programs processing fields of different types shows different patterns. What's more, the structure of the input may differ, and the program will dispatch distinct code to parse the input. For example, the variation of emachine indicates a different data structure. As shown in the figure, like the length of the address field differs as shown in the red box, which is 4 bytes for 32-bit program and 8 bytes for 64-bit program. From the three observations, we designed our solution AIFORE. AIFORE includes three modules, that is, field boundary analysis, field type classification, and power scheduling. The first two extract the format from the input, and the last one balance the power during the fuzzing. They together form an efficient fuzzing system. Then we will look deeper into how the three modules work. The field boundary analysis is composed of three steps. First, we perform an instruction level and byte level taint analysis, get the mapping between input bytes and instructions, like the green number after each instruction in the figure. Then we merge the relationship to the basic block level and get the mapping between input bytes and basic blocks. Finally, we use a minimum cluster method, get the minimum units in the parsing process as format fields, and get the mapping between fields and basic blocks, which is used later in the type classification. Now we split the input into indivisible fields and get the field boundaries, like adding a frame to the input bytes. Given mapping between fields and basic blocks, we mainly use CNN to classify the field type into 6 semantic types based on 3 features. First, IR feature, that is, the instructions related to the target field. We use the intermediate representation IR because IR is simpler than native instructions and has more clear semantics. Second, format string features. Different format strings can indicate the type of the field, like %x and %s indicate an integer and a string respectively. Third, library call features. We record some special library calls in the basic blocks like memcopy, strcopy, malloc. It also can reflect the type feature of the field. Now we get the type of fields like tainting fields with different colors. When utilizing the format knowledge in fuzzing, we face the following 2 problems. First, there are a large number of input generated. Which seed should we perform format extraction on? Because the format extraction is relatively much slower than the test case generation and execution. If we analyze each seed, it is against the spirit of fuzz testing. Second, how can we balance the fuzzing power for different format variants produce a DRM mutation? So we designed the power scheduling algorithm. To the first problem, we only focus on those valuable seeds, which means the seeds reach more new basic blocks and achieves higher new coverage, more likely belong to an unseen format variant. To the second problem, we utilize custom mutators based on the type of fields. We assign power to those seeds bound with less mutated format variants and skip those bound with the fully mutated format variants. Okay, we implement our system on many amazing tools and works. We build the taint analysis engine based on Fuser and libDFT to support 64-bit programs and byte-level taint analysis. We use Anger as the backend to support static analysis. And we implement the machine learning component with Keras. And we write an automation script to export the template result from 010 editor. And the fuzzing system is based on the famous framework AIFORE. To evaluate the performance of AIFORE, we constructed the following experiments. For the format extraction, we measure the accuracy and the time performance under different configs for different compiler optimization levels, different amount of training data, and different seed sizes. For the fuzzing, we compare with SOTA works on code coverage and bug detection capability, and performed an ablation study to see the contribution of each module. From the field boundary accuracy result under different optimization levels, we conclude that the accuracy is irrelevant to the optimization level. And for the CNN performance, first we investigate how much data is required to train a reliable enough model. We take 10K fields as unit 1. From the figure, we can see a larger amount of training data results in higher model accuracy. However, the growth rate stagnates quickly when the scale is larger than unit 1. So we use 10K fields in the following experiments. We measure the accuracy changes during training on training set and validation set. The final accuracy is over 85% and stable for different optimization levels. According to the training set, we measure the type classification accuracy for unseen formats with trained programs and unseen formats with untrained programs. From the results, we can conclude that AIFORE can predict the field type in unseen formats with high accuracy, and the module performance is irrelevant to the program's optimization levels. Combine the boundary and type modules, we compare the format extraction performance with other format reverse engineering solutions. It results that AIFORE achieves higher accuracy both in field boundary recognition and field type prediction. As for the time performance, AIFORE also has a good result. The average time to parse a file with AIFORE and tfuzzer doesn't differ significantly for different size classes, while ProFuzzer and EPFL Analyze spend much more time parsing larger files because they use a profiling method to get the type of the fields, which is exponentially proportional to the input size. For the fuzzing performance, we compare AIFORE with 6 fuzzers, including format-aware fuzzers, format-unaware fuzzers, and power scheduling optimization fuzzers. For each target program, we run all fuzzers for 24 hours with 5 times. AIFORE achieved the best performance in most cases. And the first 2 columns show the results with only boundary modules or module or boundary and type modules enabled, which is used for ablation study later. With the help of the format knowledge, AIFORE finds 34 bugs, 20 are uncovered by other fuzzers in total after manual deduplications. Finally, we evaluate AIFORE with enabling the modules one by one to see the contribution of each module. The coverage result of each module has been shown in previous slide, and as shown in the box plot, the 3 modules B for field boundaries, which help mutate bytes as a whole in a field, T for field types, which help mutate fields with proper mutators, P for the power scheduling, which helps assign more energy to those formats which are not mutated adequately. All modules compute significantly to the coverage increment. Okay, to summarize, we propose a field boundary recognition method which utilizes taint analysis to identify relationships between input bytes and basic blocks, as well as the minimum cluster algorithm to split indivisible input fields, and a novel deep learning-based solution to predict the type of input fields processed by basic blocks, and the novel format-based power scheduling algorithm to explore infrequent types of inputs. With this all, we implement our novel smart fuzzing solution AIFORE and systematically evaluated on a wide range of input formats and programs. Results show that it has a much better performance on input format recognition and format-aware fuzzing than SOTA solutions. Okay, thank you. That's all. Any questions?